Okay, question 4 on page 122, chapter 6. So this is number 4. We have a 200-gram mass, so the mass is equal to 200 grams, but we don't work in grams, do we? We got to convert it to kilograms, so we divide by 1,000, so we get 0.2 kilograms. So we have this mass, and it's oscillating on the end of a spring on a horizontal surface. So we have our unmovable wall. That's our symbol for an unmovable wall. We have our spring come out, and I'll just draw it like that. And we have a mass at the end, and it's sliding back and forth horizontally. And we don't have to worry about friction. We're told that it's friction-free. No friction. And you can be thankful for that. No friction. The spring can be both stretched and compressed and has a spring constant. We were just talking about spring constants. In this case, it's 360 newtons per meter. It was originally stretched at a distance of 14 centimeters. So we'll assume this to be the equilibrium. X is equal to 0. Then we stretch it a distance of 14 centimeters. So let's say when we stretch it, it's all the way out here. Clearly, this is not drawn to scale, but we can work with that. 14 centimeters is 0.14 meters. So you take the, what is it? It's a mass. And you stretch the spring, you're holding it, so it is at V is equal to 0 initially. V is equal to 0 initially, and then you let it go. What's going to happen? Well, the spring's going to pull it back. Going to pull it back, and as it pulls it back, this is pretty important. The spring is going to continue to pull. Initially, the spring is stretched a lot. So you have F is equal to minus KX. When X is big, do you see that F is big? So initially, when the spring is stretched this much, you have a big restoring force. The force pulling the mass to the left is large because X is large. And then as X gets smaller and smaller, right, it's 0.14 here, it's 0 here, so as the mass moves to the left, X gets smaller and smaller, so the restoring force gets smaller and smaller. Eventually, when the mass is at the equilibrium point, X is 0, so F is 0. But it still has speed, right? It has 0 speed here. We have a force moving it to the left, so it's accelerating. See, this is going back to the difference between acceleration, forces, and speeds. We need to be clear on that. So this mass is going to be accelerating to the left. So it means it's going faster and faster and faster and faster. So right now, when it's at equilibrium, the force is 0 because X is 0, but it still has a lot of speed. So it's going to overshoot the equilibrium. And now the spring's going to be compressed, and the force will now be to the right, slowing up the mass, slowing up the mass, slowing up the mass. Eventually the mass will stop because of the spring compressing, and the object then will continue to go to the right. And so the mass will oscillate back and forth. It's important you understand that concept, so don't dismiss it. Make sure you understand why the mass is going back and forth. Understand why the speed is 0 at this end and 0 at this end, and maximum when the mass goes through the equilibrium point. So from here to here, the speed increases. The speed is maximum here, and then from here to here, the speed decreases until it finally gets to be 0, and then the spring pushes it back to the right, and the mass will just oscillate back and forth. Make sure you understand that concept. Okay, so question A. What is its initial potential energy? Well, initially, it's out here. So for A, we can write the potential energy is equal to potential energy of a spring is 1/2 kx squared Remember, as the mass is oscillating back and forth here horizontally, the height doesn't change. So now we plug in 1/2. K is given to be 360. X is equal to 0.14. But X is squared. Plugging those numbers into my calculator, I get 0.5 for 1/2 times 360 times 0.14 squared equals. So I get the potential energy initially is equal to 3.53 joules. That's the answer to A. Not too bad. How about B? B, what is the maximum velocity that this mass will reach in its oscillation? And where would it be? Well, we already talked about that. The maximum speed is going to be when the mass goes through the equilibrium point, both in this direction and then when it comes back going this way. The speed will be maximum. The speed will be maximum. Remember, speed doesn't have a sign. The speed will be maximum as it passes through the equilibrium. And it wants to know what that number is. Well, in this case, we don't have friction, right? No friction. So EI is equal to EF. If we consider the initial point to be here when it first starts out, we already found out what the initial energy is. It's potential. So that would then be 3.53 joules. That's going to be equal to the final kinetic energy. Well, for this problem, let's pretend the final is right here as it goes through equilibrium. Well, that's where we know the speed is a maximum. It's the kinetic energy, because it's moving, has no potential energy because K is 0 as the object passes through equilibrium. So the only energy then is kinetic energy, the energy of motion. The object is moving through the equilibrium point. So we have one equation, one unknown. M is known. It's given us 0.2. So we get 3.53 is equal to 1/2 M, which is given as 0.2, and V squared. V is what we want to know. Solving for V, we get, all right, so let's plug this in, 3.53 times 2 divided by 0.2, and then we got to take the square root. So 5.94. V is equal to 5.94, and don't forget the units, meters per second. Okay, so that's B. Now we can move on to C. Ignoring friction, which is what we've been doing, what are the values of the potential energy, the kinetic energy, and the velocity of the mass when the mass is 7 centimeters from the equilibrium position? Well, it starts out at 14 centimeters away. This question for part C now is, it wants to know what the potential energy is at 0.07 meters, right? 7 centimeters is 0.07 meters. Wants to know what each of these are. Well, the potential energy is equal to 1/2 kx squared. Plugging in, we get 1/2. K is given to be 360 in this problem. And X is given to be 0.07, 7 centimeters. And that's squared. So plugging those numbers in, 0.5 times 360 times 0.07 squared equals 0.882 joules. What is the kinetic energy there? Well, we don't know what the speed is. So we have to use conservation of energy. Energy initial is equal to energy final. We know what the initial energy is, 3.53. And that's got to be equal to the potential energy plus the kinetic energy when the object is here. When the object is here, we already found out what the potential energy is, 0.882. So the kinetic energy then is equal to the potential energy minus 3.53. I'm sorry, it's the other way around. Sorry about that. It's 3.53 minus 0.882. We just plugged in. Potential energy is equal to 0.882 and use this. So we solve for K. KE is then equal to 3.53 minus the potential energy. So the kinetic energy is then equal to 3.53 minus 0.882. 3.53 minus 0.882. You can see most of the energy is kinetic at this point. 2.65, we'll call it joules. That's what the kinetic energy is. But the next part of part C is, what is the speed? Well, we know the relationship between speed and kinetic energy. So we write down kinetic energy is equal to 1/2 mv squared. Kinetic energy we just found out was 2.65. Well, that's equal to 1/2 times the mass. The mass was given as 0.2 kilograms. And we're going to multiply that by v squared, which is our unknown. Once again, we have one equation, one unknown. We eat those for lunch. So v is equal to, let's do the math, 2.65 times 2 divided by 0.2 equals square root 5.15 meters per second. So the speed is 5.15 meters per second as it travels through the equilibrium point. It's the velocity is plus 5.15 as it travels to the right, or minus 5.15 meters per second as it travels to the left. That's the velocity. Remember, speed doesn't have a sign. D. Part D. How does the value of velocity computed in part C, that's this right here, how does this value compare to the computed in part B? Well, in part B we found it's 5.94. So part C is less than 5.94. So I'm going to put down VC is less than VB. It wants to know what is the ratio of the values. And the way they have it is part C compared to part D. So that's VC divided by VD, because they said VC first. They said part C first. So you put the VC on top. VC is, that's B here, I'm sorry. That's B. So we get 5.15 meters per second divided by 5.94 meters per second. Notice that the units cancel. It's unitless. It's a ratio. So plugging in those numbers, 5.15 divided by 5.994 equals, S equals 0.867. So that means it is 86.7%. The speed of the mass when it's at 0.07 meters away is, let me make sure I'm doing this right. Ratio is 86.7. So B is when it goes through the equilibrium. So it's gained 86.7% of its speed. Speed here is 0. When it gets to here, it's 86.7% of the speed that it is here. It's gaining speed. That's what we talked about before. Okay, that's question D.